So what you're going to work with today is super similar to Calc AB. There's just two components to the movement instead of one. So you've been used to getting the position model, and they call it X or S, and they'll ask you questions about velocity, acceleration, total distance traveled, displacement, all that good stuff. And that's still going to be asked. It's just instead of our position and our velocity and our acceleration being a single function, it's going to be parametric. So quantities like area, volume, temperature, time can be represented with one number that we call a scalar. But when you get more into the physics realm, where you have force, velocity, and that kind of stuff, they need to be represented with vectors. The good part about it is vectors can be, there's a lot to it, but you don't learn the majority of the vector stuff until Calc 3. It's usually the first thing you learn in Calc 3 after you review a little Calc 2, is they go in and do a whole unit on vectors. So the majority of your vector work will be in Calc 3 and in physics. Our vector work in Calc 2 really resembles what it did in Calc 1. It's just we have two-directional movement. So it is going to be what you would think it is, so it makes it kind of easy. But I'm going to do the geometry of vectors first. So it's like a directed line segment like this. Go ahead and write that. I'm going to call this vector W, so because we're going to have V standing for velocity in a little bit. But I'll call that vector W. And the vector symbol is like a ray that's missing a prong on it. And when you give notation for a vector, and you should have done this at some point. Have you guys worked with vectors at all before? A little bit. Yeah, you should have. They're given in chevrons, not in the curved brackets, and they don't indicate location necessarily, because in the coordinate system it's always, okay, 2, 4 means 2 to the left, 4 up from start, from the origin. For a vector, this could be 3 and this could be 4, but you're not always starting at an origin. Sometimes you're starting off another vector. So it just gives you basically you're moving 3 to the right as you're moving 4 up, from where we don't know. Anyway, we also on here have what we call this notation, and this might be new to you, but this notation is actually, it's got several words that go with it. The most common is magnitude, but sometimes, like in geometry, they just call it the length of it. And what else do we call it? The norm. It's sometimes called the norm of the vector. But either way, all you do to find it is really to figure out how long that is. So if I were to say what's the magnitude of vector W, what's its length, what's its norm, you just use Pythagorean theorem, and it is a scalar, and it's 5. So that's all about like the position part of the vector. Pretty easy, right? So we also are going to have, you might want to write on here that to do that, we did the square root of x squared plus y squared, technically, if we're considering these x and y. But they also have speeds attached to them, which we're going to call dx dt and dy dt. So we'll have this two-component part of velocity as well. So I'm going to go down here. It says we've dealt with horizontal and vertical particle motion. They'd always tell you you're moving along the x-axis, you're moving along the y-axis. But if it follows a vector, it just needs to get a little change. Usually the position will be called s of t, sometimes it's called r of t, but never will it be called x of t for parametric. All right, so it'll be one of those two. The position one sometimes is in the chevrons and sometimes it's in these soft ones. So don't let it bug you if you see sometimes it's given like that. But you'll be given a parametric set of equations, which you're used to. So it shouldn't be a hard transition. It might say x of t equals cosine t, y of t equals 4 sine t. And maybe it traces the path along an ellipse. So these will be given parametrically, so let's write parametric. That just tells you what it's always told us, though. Where is it at any given time t? So you're used to this. A particle's moving along the x-axis, and x of t is given by 6t squared plus 4t. What's its velocity at time 1? And you would say, well, my velocity is 12t plus 4. So at 1, it's 16, and you're done. Correct? we're going to still have the same concept, but we will have an x of t and a y of t, and our velocity will be given in two components. Its name is going to be like that with the vector symbol over it. So the velocity vector is what you would think it would be, but it is a vector, and so we put it in those chevrons, and it is what you would think it'd be. What do you think this component of it would be? Dx dt, yeah, or x prime of t. So dx dt will go here. You know how to take derivatives with respect to time, and then this one would be dy dt, just like you would think. Notation-wise, sometimes we'll call that x prime. Sometimes we'll call that y prime. Sometimes they even call this the velocity 1 component, and this gets called velocity 2. I'm just trying to give you all the notation because I don't want you to be, we're not book dependent because we don't have a book, but you could see it written in any of those three. But really you just take the derivative of the position. Position's just going to be given as two separate functions. So likewise, guess what we say the acceleration vector is? Second derivative of the position, or the, yeah, let's write it like that. So you could say d squared x dt squared, d squared y dt squared. Second derivative of position, you might see it as x double prime, y double prime from here, or you might see it as v prime of the first velocity vector and v prime of that, but it's really, you'll just take the derivative again, like you always have. And it's a vector as well. And it still tells you the same stuff. It tells you how the velocity is changing. It's just you have two components to the velocity. How fast am I being pulled this way and how fast that way? Do you kind of get it conceptually? So you're going to have two things pulling on your particle that's going to have it moving along vectors. So the magnitude or the speed of the velocity vector, let's go ahead and write that down. I'm going to go back up to the top. So right here, if I were to talk about the velocity, again, this 3 isn't going with the dx dt. That's just me saying it moved 3 to the right, 4 up, and this is the length of the segment that would then be the length of the vector. But if I were to talk about the speed of it, that deals with the velocities. It's really just like using the Pythagorean theorem on your velocity vector. And it's called the come on, plus sign. There we go. My finger was in the way, I think. All right. Come on, boom. When it talks about the magnitude of the velocity vector, the magnitude of this vector would be 5. The magnitude of the velocity vector would be the same thing, except I'd just be squaring the derivative. So it's just on another level. If I said, what's the magnitude of the acceleration vector? If your acceleration vector is -2, 5, right? The magnitude of it would be the square root of 4 plus 25. It's really just how long it is. Are you good with that? So when it says the magnitude of the velocity vector, also known as speed of the particle, you'll do the square root of dx dt squared plus dy dt squared. Now this should look familiar to you because this is part of a formula. What formula that you already know is it a part of? Arc length. Now watch. Don't write this down because it's coming at another page, but if you get how the tie-ins between this stuff and what you already know, if I were to do the full arc length formula, it'd look like this, correct? And then this is what's embedded in it with respect to time. Agreed? I just told you that that's the speed of the vector. What did you used to call the speed when it was just one direction? Absolute value of what? Velocity. And last chapter, when we would integrate the absolute value of velocity, what was this a formula for? Total distance traveled. It should make sense that I'm going to get the same thing. It's just instead of calling this arc length in parametric, we'll call it total distance traveled. But it's the same thing. We'll be integrating the speed. The speed is this, and it's really the arc length formula. So when we talk about the total distance traveled, you already know it. That's what you were doing when you did arc length. Are you good with what I just said? Because there's a ton of formulas, and we don't want to have to commit a ton to memory. So I'm going to give you just a second or 2 or 5 or 30 to read this page and see if there's anything on here, just notation-wise, because This has a lot of stuff on it, but I think it's all kind of, I know that. Go ahead and read it. That's okay. Anything on there we need me to clarify? What do you think? Are we good? No hands up? All right, I'm going to have you go back to the velocity one and just put a little note on here. You're also going to be asked the question, when is the particle at rest? You're used to that question, right? We've always said, last chapter, we said a particle is at rest when its velocity is 0. Whether it's changing directions or just stopping and going forward, it doesn't matter. It's at rest when its velocity is 0. That holds here, but you have to be careful because you have two directional movement. So when your velocity vector is this, it doesn't mean that it's at rest. What would that mean? Just in terms of common sense, if that was your velocity vector, how is it moving? Straight down. Exactly, due south. It means there's no horizontal velocity and a negative vertical velocity. So we have to be very careful with that. When it says when at rest, so let's go add this. When at rest, if that's the question, what do you think needs to happen? What do you think? Yes, they both have to be 0. So you will have to set dy dt equal to 0 and dx dt equal to 0 to determine the times at which, right, the particle is at rest. So just be a little careful with that. Otherwise, it's all kind of the same stuff. So I'm going to go fairly quickly through some of this and maybe even skip a little because it so ties into what you already know. So we have a particle moving around the xy plane. It's not moving along the x-axis. It's following this path. You should be comfortable graphing that on your graphing calculator. You should know that you go to parametric mode. We've done all the pre-calc of it. The question is, what's the velocity vector? Well, all you do is say it's got a horizontal component, which is the derivative of position, and a vertical component, which is also the derivative of position. So nothing difficult there. Same as always, when you want to do it at a specific time, you just plug that time in. You will get a two-component answer right now. It is a vector that's got an 11 when I put a 1 in and a 1. That's it. That's the velocity vector. What does that tell me about how the particle's moving? It's moving very fast to the right and slowly up. So if I were to graph that, which I'm not going to, my guess is it's kind of going like this, like it's moving to the right way faster than it's moving up. All right? Just so you get the concept of it. When it says, what's the magnitude? This is always a scalar. It's a numerical answer. It really means how long it is. It also gets for the velocity vector, it's the speed. So the magnitude of the velocity vector, sometimes it's written like this, but notation they don't always. Actually, I know AP doesn't have this notation on it, but this means magnitude when you put it, it kind of looks like absolute value inside of bigger absolute value. So the magnitude of the velocity vector is really just how long is it. So this would be the square root of 122. Now there's more physics involved in this than we're getting into. I'm giving you the basics, the formulas, more than the calculus you'll be asked, but really there's a lot to vectors. There's like forces and centrifugal force, and there's other things that affect this movement. We're not going there. Are you all right with that? It's moving in a vacuum, let's say. So it is simply moving with nothing else affecting it. When it says what's the acceleration vector, you'll just say a of t. It is a vector. Boom. And what do I just do? Take the derivative. Yeah, can you do that for me? Because I can't see them anymore. Give me a quick derivative. Go ahead, Sammy. 6 plus 8, comma, minus 6t, are we good? I can't see the functions anymore, so I'll just take it at face value. And then when it says at time 1, well, you just shove it in. It's kind of boring because there's nothing new right here. It'd be 14 comma 6. When it says what's the magnitude of it, what do I just do? What do I just use? Square root. 14 squared plus 6 squared. I don't know what that is. The square root of 196 plus 36. And again, it would be written if I wanted to use formal notation to get you used to it. Honestly, I don't really care right now because you're going to learn that all again in another course anyway. But this would be the magnitude of the acceleration vector. It would be this. And I'm not going to simplify roots and all that good stuff today. What do you say? Are we good so far? Nothing hard, right, Mo? So far, so good. Next page. So go answer this question right now. You could almost do it in your head, but write it down a little bit. Mainly, I want you to know what they're asking you for, understand how it ties to what you already know from Calc 1, and try not to memorize anything. And you'll be fine. Actually, kids usually think parametrics are easy. There's usually one in the FRQ, but last year it was a polar. But it tends to be more parametric that you get asked than polar, which is nice because polar's hard. Harder than this. I'm just going to go like this. Magnitude of the velocity vector would equal, it's a scalar, it's a single number. I don't know what it is. What is it? Can someone tell me? It's 6? Can someone back that? What'd you get, Amanda? I just need a backer. Well, I'll go do it. It'd be 2t plus 3 in the horizontal component, 3t squared minus 6t in the vertical, right? I'm doing it at 1, right? So I'm seeing a 5 and a negative 3 as my components. Oh, well, and let's stop here. What does that mean about the particle? How is it moving? To the right faster than it's moving down. So that's kind of what causes an ellipse to turn. You know what I mean? And become, it moves down, but it's moving to the right faster. When we do the next one, it is an ellipse. Why? Well, here, let me write the answer to this. Hey, what would another question have been that, how could I reword this question and have it give me the same answer? I could have said, what did I actually just find? Speed of the particle. Yeah. So, that's the same stuff, trying to get used to the language. I said we're going to do an ellipse, and this is the whole reason I did the pre-calculus of it. So you would look at that and perhaps recognize that that's an ellipse. How could I get the, eliminate the parameter on it? You could, right? We know how to do that. That's fair game for the next test. Eliminate the parameter on this. We could. It won't give me a circle. It's being pulled farther along this axis than this one. So I know, let's go over here, by the way. I think it's on the next page. Does it say to graph it on the next page? Maybe I'll wait. Yep, so we'll wait. It says find the velocity and acceleration vectors. Let's go do that. My velocity vector is just simple derivatives, so negative 4. I'm going to take the derivatives fast just to, there's a lot of notes today. I'm really doing a week's worth of AB in 35 minutes just because you've had to wait so much of this. All right, so I just took the derivative at pi over 2. Let's not rewrite. Let's go pi over 2 here, pi over 2 here, pi over 2 here. Boom. What do I get? Tell me what my component is. Go ahead, help me out. Negative 4, right. Negative 4 comma 0. All right, so knowing what you know about first and second derivatives, what would dy dx there be? Think about it. What? 0. dy dx is dy dt over dx dt, correct? So that only means I have a horizontal tangent line there. It doesn't tell me how things are being pulled or how they're moving. Just want to make sure you understand the difference between dy dx, right? That's just the slope of the tangent line. And I'm telling you that will be 0 at pi halves. So to verify that, let's go graph it right now so you can see it. So I'm going to draw the path of the particle. I'm not going to eliminate the parameter because that's why we did the whole pre-calc stuff, so you'd understand what I'm saying, understand how I know it's an elliptical path. It is nice to know where it starts. So if you guys could plug in a pi over 2 to the original position function, and tell me where I'm starting. It's usually at one of those quadrangle marks, but I want to know if I'm starting at the top, the far right, the left. That I need to know, but I don't see any negatives in there. So generally that probably means I'm starting here, but can you verify that for the position? Is that where it starts? Nope, at 0. Yep, is that where it is for position? Starting at 0, 2? No, at 0 it'd be at 4 and then 0. No, I'm right. I'm good, right? I'm looking at the position model. All right, so it's going to move like this. Now keep it, oops, I'm going to turn a little, boom, like this. I'm going like that. What I just am talking about is at this moment in time when it's coming around and hitting at time pi over 2. There's a couple things to notice. I do have a horizontal tangent line. dy dx is equal to 0. It's dy dt over dx dt, and that would be 0. Just to give you a little flavor of what the vector notation stands for, we said that the vector is, we said 0, was it negative 4, 0? What was the velocity vector? Really a better notation for that, and that's where the physics comes in so you understand it better. It's not in our calc book and you don't really need to know it, but when you say that this is the velocity vector, a good adjective to put in there is they call it the tangential velocity. So it's like it's coming off the end of here and nothing's pulling it down, it's just flying off the end. Kind of like if you were on a roller coaster and you were going up and you just kept flying right off of it, that's what you're finding. It's called tangential velocity. So right here at this, it's being shoved that way and not down. But guess what happens as it starts to come around here? Watch. We're going to stop for a second. Go to 3 pi over 4 and give its velocity. This was at pi over 2. Find the velocity vector at 3 pi over 4. It shouldn't shock you what you're going to get. How do you think it's getting pulled? Down and to the left. Do you think it's getting pulled to the left faster? Look at the shape of it. Or down faster? Look at the shape of the ellipse. If they were equal, it'd be a circle, right? Exactly. So what I'm going to get, if I get what you're, it helps. Honestly, you could do this all without having a clue what you're doing, and you'll do great. But the physics behind it, I guess, is somewhat interesting. We will get negatives. I know this number will be greater because I can see that it's being pulled faster that way. That's what's giving it that elliptical shape. Go do it, though. And what am I doing? I'm going to the velocity vector and doing it at 3 pi over 4, not the position vector. That'll tell me where am I right here. Don't want to know that. I think last hour, this one was negative root 2. I don't remember what the first one was. I had them do it as negative 2 root 2, you're telling me, Noah? Okay, so this over here is negative 2 root 2. If you don't understand what that means in the context of the problem, you'll still be very successful. But I hope you have a little flavor of why I said they're both going to be negative. I can see it being pulled to the left and down. Why I knew this was going to be greater in absolute value, and it's because that's what's making it an ellipse instead of a circle. Are you good with that? So had my path been just cosine sine, guess what happens at 3 pi over 4 with the velocity vector? They're the same, but over there they'd both be negative. Do you see what, so just so you get it. All right, so back to the previous page. Do you need to understand the physics of that? Not particularly. It says to find the speed. You should do that in your head. If I were to say right now, what's the speed of it at pi over 2? What would you say? 4. Why? Why? Yeah, I mean, it's the square root of 16 plus 0, plus you might even consider it more. It's the one directional movement, so it's the absolute value of velocity, right? That would have been a particle is moving along the y-axis, or x-axis, sorry. So same thing, but we're done with that. Let's move on here. What do you think, Mo? You got it? Yes. When it says AKA, what else do we call arc length? What am I going to call it in parametrics? I could have asked this question 3 days ago in arc length, but now I'm going to just rephrase it. Find the arc length, also known as what? Yeah, there you go. Total distance traveled is how it might be phrased in this scenario. Total distance traveled. Now, I'm hoping you don't need to look back at that, because if you really get it, you can just create the model without having to memorize anything, because it's what it's always been, right? Arc length. What do I do to get it? I integrate. From where to where? 0 to pi. What do I integrate? Well, for parametric, the square root of what? Dx dt squared plus, yes, I already know that one. We already proved it. We derived it. We're good. Another way to think about it at almost a better level, which I already told you, is to understand that this is actually the formula for speed, which is the absolute value of velocity, which is the model you've always known. Does that make sense, Molly? Because then we don't have to memorize stuff. That's the kicker for this chapter. When we're done, we're going to have so much stuff because we're not even to polar yet, and there's all kinds of polar formulas too. So, all right, so let's go back up here. So I already know the velocity vector. Super important, honestly, this is the one that you're usually given. So I'm going to put given most of the time. By who? By College Board. We're all AP today. Some days we veer from AP. Today is 100% AP Calculus. I don't even know that they discuss this a whole lot in like a regular non-AP one. All right, here we go. So the velocity is what we always think it would be. Let's call it x prime of t, y prime of t. Makes it a little easier to write. Now, let's go back to the rectilinear motion. How did we say you would get displacement if you knew velocity? You should be able to think back to it. We're going to do the exact same thing. How do we get displacement, which is really just change in position? What do we integrate? Just naked velocity, no absolute value, right? So we will. The only difference is we have two components to it. So I will integrate from t1 to t2. Whatever time interval they want me to figure out the displacement on, I will integrate. Guess what's going right in here? Because I get it, because I've done it before, kind of, right? What's going here? Yeah, the velocity, horizontal component. Or you could call that dx dt, or component 1 of the velocity. That's kind of up to you. I like the prime in this scenario. What do you think's going right here? Yeah, same thing. Y prime of t. What does that give me? Like if you were to think about it, this would give me x of t, so it'd give me x of t2 minus x of t1, the change in the horizontal component. Makes sense, right, Megan? All right, so the next one, total distance traveled. See if you can have it down. I already told you what it is, but throw it on there again. Should not be memorized because we totally get it. How have we always gotten it? Or it's also known as arc length. My biggest challenge is really not to get you to do the math. It's to get you to not have to memorize stuff this chapter. All right, so Noah, what's total distance traveled on a given time interval? Integral. T1 to T2, then what? But, no. You're thinking the old non-parametric stuff. If I wasn't in parametric motion, I totally agree with you that I just take whatever they tell me the velocity is and I do the absolute value of it and I'd be good to go. The problem is I have two velocities I'm working with. There we go. Now we'll tweak it. Square root of what? There it is. There. What he said, though, should trigger this formula, because he said, I'll integrate the absolute value of velocity, and that's the speed, and this is how we get the speed. So it's all good. Now, the next one's the hardest question, and probably the most asked. So I think I'm going to take it. This is the kind last chapter where they'd say, find the position at t equals 5. What did they have to tell you? A starting point. It didn't have to be at time t equals 0, but it had to at least be before 5. So let's do this. Let's suppose I tell you what t of 3 is. All right. At t of 3, let's say this. S of t, or S of 3 is, here's the difference. It's now 2 components. So I will tell you that it's not sitting at 1 or at 4. I will tell you its position is, and sometimes it'll have chevrons, sometimes it won't, but let's just use those because I like it. What am I telling you? It's 2 to the left and 4 up. Okay, but not at the start at t equals 3. What they'll do is they'll say find the position of the particle at t equals and maybe 7. Now think of what you would do last particle motion chapter, a la AB, and we're going to do the same thing. We would take whatever I told you it started at. Suppose I said S of 0 is 2, and I wanted you to figure out S of 4. You would say 2 plus, and then what would you do? You'd integrate. From where? 0 to 4, that time gap. Of what? What would you integrate? Because that's important, because we're going to do the same thing. What would you integrate? Velocity. Exactly. Really what you're saying, though, it helps if you have a conceptual. This would have been last chapters. Don't write it down. But really when you integrate the velocity, you're getting displacement. So it's where was I, and then how much was I displaced. Makes sense, right? If I'm already at 2 and I was displaced -7, I'd be at -5. It's the same thing, but we need 2 components to it. It gets tricky. So here's how I'd figure out where I am. I'm going to use a generic one, because if I use all the T1 and T2s, it's like alphabet soup up here. So where am I after time 7? There are 2 components, a huge gap to where I am. This can be very difficult if you don't get how it all fits together, David. Are you ready? So let's just do, this is all about where am I horizontally? Where did I start? -2. Then I have to figure out how I was displaced horizontally. On what time interval for this problem? 3 to 7. And I'm creating it. I do not memorize these. And what do you think I'll throw in that integrand? X prime of t, also known as dx dt, also known as v sub 1 of t. But I like x prime in this scenario, so if you're okay with that, I'm going to go like that. Is that anything new, Sophie? Not really. Right? Over here, write what you think is going into my vertical displacement component. The language is like, it trips me up. I'm making sure I'm phrasing everything correctly. And what does this model tell me? It tells me where I am on that, if it was an ellipse, where I am on the ellipse at that time. Not how fast I'm moving. What'd you write? Go ahead. Go ahead, Dootsy. Excellent. Okay, what do you think about that, Cole? You said, is it just a tweak of AB? And I'm like, yes. I mean, it is, but the AB certainly helps. If you don't have your poop in a group with SVA on the AB level, this is a nightmare, right? But you guys are really good at it, so I think we're great. We'll go do one. I'll give you the velocity and ask you several questions. Go do part A, that's easy. But I'm going to ask you to move all over the place without looking at any formulas. If you have to look, you don't get it. Should be quick. Pop up a hand when you have it. Should be 2 components. I'll write them down. A of t, let's just do A of 3 equals blah, blah. Addie Mae, what was component number 1? What did you say? Let's do it at 3 though. So e to the third minus 3, e to the third plus 3, right? Now we'll talk about calculator active. If these are calculator active, it means whatever's here would be impossible to derive, too long to derive, or just don't derive it. What would you use? Oh, minus 1. Sorry. I was doing it in my head and I'm getting sloppy. Sorry, 1, 1. So if I had a calculator active question, what would I do to go from here to here and get my 3 decimal rounded horizontal? I'd math 8. The X's in my math 8 are really the what's in this, T's. So you have to be, you're still in function mode while you do it, right? Or in the parametric second calc, didn't it have a dy dt option? So you could graph it and then go do that off the graph. But I think it just math 8 it in your function mode. All right, so that's easy. Addie Mae, though, what if it said the magnitude of the acceleration vector? Then what would I do with this? If I just said find the magnitude of the acceleration vector at t equals 3. What does that mean? Square them, add them up, take their root, round to a minimum of 3 decimal places. It won't ask that on this type, but just so you have it. Now I want you to set up a model to get the position, but not actually integrate it right now. But just without looking, how would I get the position at time 3, which we'll still call S of t. Some books change that to R of t when it goes vector, but it's the same. It's usually a pretty big, takes up some real estate when you write it out. Pop up a hand when you just have it written. Don't actually do the integration. Got some over there. All right, Mo. Horizontal component, have at it. Perfect. Assuming that the horizontal initial position was at 1 and I'm not looking, and that was at time 0. All right, because I can't see the directions anymore. All right, Lindsay, go ahead. What's this one? Yeah, let's just do that. Now, the y prime of t, where am I going to get these from? That's my what? Velocities, right? Which they gave me. So let's go do that. This would be 1 plus antiderivative of, this was e to the t plus t, right? Minus t for the first one. And then this was 1 plus 0 to 3 e to the t plus t for the second. Perfect. It'd be very reasonable for you not to have a calculator for this. Right, Billy? Super easy antiderivatives. But if it's calculator active, who do you go to right now? Math 9 in function mode where this t is your x. I'm feeling good. You got it? It's a lot of info to take in today, but that's okay. We get lots of time to work coming up, as long as you're listening to me. All right, antiderive this for me, Sammy. 1 plus what? Yep. Yes, and I would block the whole thing off from 0 to 3 so you know that the 1 is not part of the subtraction in your fundamental theorem of calculus. Then 1 plus ditto e to the t plus t squared over 2 from 0 to 3. I'm assuming you could evaluate that, so can I quit? It ends up being e plus 9 halves, I think, and e minus 9 halves or something like that. So nearly done. I'm not going to, this is for tomorrow. I'll talk about all that tomorrow. But some of you might want to start on your homework today, and there's one I want to discuss, unusual questions. So I try to find worksheets online that are right in the middle. If they're all too easy, we don't learn enough. If they're all too hard, we get too caught up in the mechanics. And I like there to be some weird ones. Sometimes I have to add my own stuff, sometimes not, but there's one on the worksheet, the first one I found that's like this. It's a great question because you have to really understand what you're doing. How is this one different from what I've been talking about today? What'd you say? Right, it's not parametric. Okay, and you're not going to parameterize it. I haven't even taught you how to do that. However, you can still work with it because we have a relationship between our y as a function of x, dy dt, and dx dt. What's the relationship between y, x, and those two? We have one. What is it? There's two ways I can approach this. What'd you say? No. There is a formula that we have that involves this, and something I can get from that. Maybe that's more helpful. What'd you say? Oh, even dumb it down one more. The first derivative. Exactly. There's a couple ways we could do this. We could be, here's what I like. dx dt will equal, no, let's not even do that. Let's go like this. dy dt equals dy dx times what? Just think of unit analysis. Times what? dx what? dt. Or, like Megan said, we know slope. dy dx is dy dt over dx dt. It's the same equation, correct? But you need a relationship between them. What did they give me? They said dy dt is 5 when x is equal to 2. How could I figure out what dy dx is? Take the derivative. I would even choose not to go implicit because this is so, implicit's fine, but this is so easy to solve for y. I'd say y equals 12x to the negative 2. I could easily do dy dx, right? Just straight up. So again, it's this relationship right here between the three. But dy dx, what do I have? Would be negative 24 over what? X cubed when x is 2. What's my numerical value for that? Are you following me? Are you with me, Noah? You're with me. Negative 8. So let's go back over here. dy dt is 5. dy dx is negative 8. And I'm looking for dx dt. Negative 3. Sorry, I'm dividing by 8. Yep, sorry. Dividing by negative 8. Negative 3. So what's my answer? Negative 5/3. That's a twist, and I like it. Okay, but Megan kind of got us started when she said, well, you said second derivative, but first derivative, do you see why, Sophie, I could have started with that full relationship, dy dx is equal to, right? And I could have worked with that too, numerically, but I needed a relationship. I'm going to be done. I'll give you worksheet number 4. You can do some of it you'll get stuck on. It's not due tomorrow.